we're going to use the process of radioactive dating using carbon-14 for this problem. And carbon-14 will decay into nitrogen-14 and produce an electron. So you can detect how much carbon-14 is in a sample of carbon by using a beta detector, or you could use a mass spectrometer for it. And by detecting how much carbon-14 there is in your sample now, you can figure out how long it's been since the whatever you're measuring had the expected amount of carbon-14 in it. So it has to be something, clay, bone, something that has carbon incorporated into it somehow. Or if it doesn't, then you have to use a different radioisotope to do your dating. Now let's look at the information here. It says it's a first order process. So as soon as you see first order process, you're not necessarily thinking radiocarbon dating, you're thinking, what mathematical formula do you need to do this? And that's the first order equation that I put down below. And one thing that looks different, this is not in terms of a concentration. And we've been using concentration so far. Well, with the radioactive dating example here, you can think of this as a concentration problem and just work it out that way. But you're really calculating number of atoms and years and things like that. Well, let's see what the problem gives us so we can figure out what we need to calculate. Oh, do we have the rate constant? Yes, we do. We have that. Do we have the time? Yes, we do. 50,000 years. And do we have the initial atom count? Yes, we do. So what are we looking for? Oh, it says how many atoms. And that's bound up in natural log of atoms. Well, one thing at a time. Let's solve this equation mathematically for the natural log of the atoms, and then we'll worry about how to tease out atoms. We'll put in our rate constant. Don't forget, it's minus the value of the rate constant. So a reminder, you can't have negative times. If you're going from final to initial concentration, that has to decrease. So keep those things in mind when you're looking at your final answer. We've got the time and year. Oh, shoot. Okay, the times and years, but the rate constant was given to you in per second. So we do have to do a seconds per year conversion. And here we go from seconds to hours to days to years. And if you're worried about leap days and things like that, a few days we're not going to worry about over 50,000 years. Let's check units. Okay, we put that in right. So now we've got our rate constant converted from per second to per year. So now we can throw in the time. There's our 50,000 years. And notice how the units all cancel. I'm going to bring that up again in just a moment. That's very important though. And we're still missing something. We need the natural log of the initial atom count. So where are we now? Let's do some math. Okay, so let's do that first part above. The 3.84 times 10 to the minus 12th times 3600 times 24 times 365 times 5.00 times 10 to the fourth. And don't forget the negative sign. And then the second piece of it. Now the units. At this point, there can't be any units, because when you take the natural log of something, you get a number back, and that number can't have units in it. So that's why it was really important up above to make sure that we had the proper units and they all canceled out. So this is where we are. We're not done, but we do know that the natural log of the atoms after 50,000 years is equal to 23.19. But that's not what we want. We want the atom count. So our problem is this. We've got the atom count, which I'm taking as x, is stuck inside a natural log. And you can't do a simple divide or multiply to tease that out. What we have to do is look for an inverse function of natural log. Now take a look at your calculator. For most of the scientific calculators I've worked with, the natural log and the exponential functions are on one key. A lot of times you'll see the natural log on a key and then the exponential e to the x function on there. And you probably have to press a shift or a second or a third button to get to it. And the reason why we need that is this. E to the natural log of x is defined to be x. So that's what we do. Let's take our natural log of atoms at time t is equal to 23.19, and we'll take e to that. Now remember in math, whatever you do to one side, you do to the other side. So we have to go e to the 23.19, and that gives us 1.18 times 10 to the 10th, well, atoms. Need to add the word atoms on there. Now, as far as the final answer, it's 10 to the 10th. Look back up. Our original count was 10 to the 12th. So it went down. That seems reasonable. Now, a couple other things as far as why I chose these numbers. That 5.00 times 10 to the 12th starting number, I got that because approximately 1 out of every 10 to the 12th carbon atoms is carbon-14. And that means I started with a sample size that has approximately 100 grams of carbon in it. And this final sample size has about 0.23 grams of carbon in it. So not a lot of carbon left. And that was the reason why I picked 50,000 years. Radiocarbon dating is limited to around 50,000 years, which is a heck of a long time, but it's nowhere near millions of years. And that's because, based on how carbon-14 decays, after about 50,000 years, your sample size gets so small that it gets very hard to detect the remaining carbon-14.